what should it have been? Can you see what's wrong? I mean, I haven't explained it to you yet. But, yes. I've forgotten to put the plus symbol in, which is the thing I meant to put in. I haven't told you what the output is. That wasn't really a fair question. But what I meant was to stick together 3 strings, not 2 of them. So the idea is that plus plus here is the operator in Haskell that takes 2 strings and concatenates them. And what I meant to say was the semantics of an add is the semantics of the left part, the semantics of the right part, appended, concatenated, but with a plus character in the middle. And then parend, what parend does is it takes a string and concatenates, takes a string S and it puts an open parenthesis on the beginning of it and a closed parenthesis on the end of it. So what's going to happen here is it will take the this string 4, this string 5, make the string with 3 characters, the 4 character, the plus character, the time character, and then it will parend that and make the string with an open parenthesis character and a 4 character, a plus character, a 5 character, and a closed parenthesis, and make this string with 5 characters. That's the semantics of this part. The semantics of this part is the string with 1 character, 3, and then the semantics of the whole thing is the semantics of this with a plus symbol, and the semantics of that, parend, so this gives me the string with, that's got 5, 6, 7 characters in, and then it'll stick parentheses on the outside. So it'll be a string of length 9, open parenthesis 3 plus, open parenthesis 4 plus 5, close parenthesis, close parenthesis. So with those 9 characters. So, and that's deep embeddings. Your language, the syntax of your language is just a term in an algebraic data type. So here's my, oops, there we go. This is the syntax of my programming language, and the syntax is nothing more than defining some values, some term of type express, some value in this algebraic data type. And the semantics is defined by defining a recursive function. So like eval is a recursive function over this algebraic data type. That's a semantics. And because the semantics sort of sits alone as a function, you can define a second one as well. So the fact that I've got a function called eval doesn't stop me also having a function called print. I've got 2 functions now, 2 separate semantics for my language. That's easy to do. So there you are. You know about deeply embedded domain-specific languages. That was not difficult. So now where the shallow embeddings come in. So these seem a bit odd at first, but they're quite popular and quite useful, and they're particularly useful if you're concerned about efficiency, which I'm not particularly at the moment, but I'm going to show you how the techniques work. So the trick is to just throw away the syntax and leave yourself only the semantics. So I want to write expressions in my language, but I don't want them just to sit there and be recursively structured trees of some kind. I want them actually to do some work. I want the terms in my language actually to give me their semantics straight away, rather than me having to do a separate pass in order to work out the semantics. And here's how. Instead of using this algebraic data type as the well, you might call it the semantic domain. It's not. That's a different use of the word domain there. instead of using an algebraic data type as a representation, I'm going to pick a different type as the representation. So here, with the deep embedding, the representation of my programs, is the algebraic data type. Now I'm going to pick a different representation. My representation is just integers. I'm going to represent the program only by an integer. And it's kind of obvious what representation that will be. A program of this form, val 5, will be represented by the integer 5. And that's what this program says. It's now not an algebraic data type, it's just a type synonym. My shallow embedding of expressions, the representation is just integers. And val takes an integer and makes one of these expressions. Well, an expression is just an integer. So it takes an integer and gives you back an integer, and it does it in the simplest possible way. It takes an integer and gives you back that integer. And add, as before, it takes two expressions and gives you back an expression. But now, each of these expressions is just an integer. That's what the type synonym says. So add takes an integer and gives you back an integer. What's it going to do? It's going to add them together. So the only difference in the syntax of my language now is that instead of writing these things with an initial capital letter, capital A for add and capital V for val, which is what I need to do in Haskell, I write them with an initial lowercase letter. That's just an oddity of Haskell. But apart from that, I write the same program. So what I would write, instead of this bit, I write a lowercase v, a lowercase b, a lowercase v. I can't do that quite as easily, but a lowercase a, and a lowercase a. And that's now a program in my shallow embedding. Now, that works okay for one particular semantics. I've chosen the evaluation semantics as the semantics I want. And you see that implicitly in the fact that integers are the representation. You see it explicitly in the fact that the evaluation function is now just the identity function. There's nothing more to do if you want to evaluate this. This, of course, is straight away 12, and if that's what you wanted to learn, then there's nothing more to do. So to evaluate, you no longer do anything. There is no syntax anymore, there is only semantics, and so the semantic interpretation is the identity function. So that's a shallow embedding. Here's a different shallow embedding. Again, doing the print interpretation this time. So instead of representing these things as integers, I can represent them as strings. So there's a type synonym. My second shallow embedding of expressions is as strings. And there are two functions, val and add. And note that they're not recursive anymore, because there is no recursive structure anymore. They're non-recursive functions. But so val has to take an integer and make an expression, and add has to take two expressions and make an expression. So val takes an integer and makes an expression by using show, and add takes two expressions and makes an expression by gluing them together correctly this time. That's what I should have written last time, with the plus in it. And again, the semantics is the identity function. Now, print is supposed to take an expression and give me a string. Well, expressions are just strings. That's what this says. So print takes a string and gives me a string, and it's just going to be the identity. So that's a different shallow embedding. So if you only wanted one interpretation, one semantics of your language, the deep embedding doesn't give you very much. You have to build this tree and then consume the tree. But it does make it easy to have two interpretations, because you just have two separate ways of traversing the tree. If you only wanted one, then you might as well just cut straight to the chase. You might as well just represent your the terms in your language by their semantics. But now I have a bit of a problem if I want two interpretations. So here, expr1 is one semantic domain, one interpretation. If I wanted a second one, I have to start from scratch and I have to redefine what val and what add do. These are the 3 points we had before. Shallow embeddings discard the syntax, there's only semantics. I don't need a separate semantic function, they're all just identity functions, that's not very exciting. But now I have a problem. What if I want a multiple interpretation? What if I want evaluation, so eval and print? I want both of those. What should my representation be? It can't just be integers, because then I can't reconstruct a string. It could be strings and then I could reconstruct the integer. So in that sense, print is perhaps a more basic interpretation than eval, because given the print, you could do the eval, you could compute the eval out of that. But in general, I'm going to have several different interpretations, none of which, I mean, aren't all interdefinable. So I have a problem with multiple interpretations. So, what can you do? Here's a simple technique. If I want two interpretations, I'm going to pick a different, another semantic domain, a third semantic domain. This time, I'm going to represent expressions not as integers, not as strings, but as pairs, consisting of an integer and a string. And then val needs to take an integer and make one of these expressions. Add needs to take two expressions and make one of these expressions. And this is how they do it. It's not difficult. So let me first introduce these two functions here. Now they're a little bit more complicated than they used to be. So eval with the first shallow embedding was just the identity function. Print with the second shallow embedding was just the identity function. But with the first shallow embedding I couldn't do print, and with the second shallow embedding I couldn't do eval. So now here's the third shallow embedding, and these become a little bit more complicated, but the beauty is you can now do both of them. So your shallow embedding is a pair consisting of an integer and a string, and if you've got one of those and you want to make an integer, what can you do? Well, you just take the first component of that pair. That's an integer. If you've got one of those pairs and you want to make a string, what do you do? Well, you just take the second component of that pair. That's a string. Easy. Now, val is supposed to take an integer and make one of these pairs. If the integer is n, it makes the pair whose first component, the integer component, is n, and whose second component, the string component, is show of n. Add should take two expressions and make an expression out of them. Each of those expressions is a pair. So I've got an integer string pair and an integer string pair, and I want to make an integer string pair. To make that integer string pair, I need to make an integer and I need to make a string. To make the integer, I've got two integers, I just pick them out and add them together. So eval picks the first integer out of it picks the integer out of the first pair, eval picks the integer out of the second pair, and you add them together. And print picks the string out of the first pair, print x picks the string out of the first pair, print y picks the string out of the second pair, and just puts them together using paren and plus in the same way as before. So with shallow embeddings, I can have two interpretations if I want. Not difficult once you see how to do it. Better if you have lazy evaluation. So Haskell has lazy evaluation. Did you talk about it? No, right. Okay. So the idea with lazy evaluation is when you might expect. So now, a term like this, add and val, using this definition of add and val, is going to generate a pair. It's going to generate a pair with three, that's the string 3, the pair with 4 and the string 4, the pair with, and overall, they're going to be the pair with the integer 12, and this string. It's going to generate a pair. Now, if you only wanted one of those, that seems wasteful to generate this pair and then chuck half of it away. You've wasted a lot of computation. What lazy evaluation does is it never runs anything until you really need that result. So you can define the steps that you would need to take in order to produce the pair, and then say the final step is going to throw half of that away. Lazy evaluation will only evaluate the things that are demanded, and if one half of the pair is not demanded, it won't be evaluated. It won't be that part of the program won't be run. So under lazy evaluation, you can generate a pair. So in this case, you'll generate the pair consisting of the integer and the string. But it won't actually do all the computation for that. If you only wanted the integer, it won't do the string stuff. That will just never happen. So if you only want one interpretation, then you'll only compute that one interpretation. So I can have two interpretations. What if I want three interpretations? Well, I can define a syntax that has not pairs, but triples of things. And then I need to pick the first thing out of the triple, the second thing out of the triple, the third thing out of the triple. What if I want 10 different interpretations? Well, then I need to deal with 10 tuples. That's getting a bit messy. What if I don't know how many interpretations I want? Maybe I want to allow myself to add new interpretations as time goes by. Then I don't even know what syntax what representation to use. It's not pairs, it's not triples, it's not tentacles, it could be any tuples. I need to define something. You might imagine doing these as lists, but it's a bit complicated by the fact there would have to be lists of things of different types. Or extensible records or something, but it's getting a bit clunky there. So we want to do something different. And this is where the higher order functions come in. So the trick here is kind of a general trick in computing, is to look at various similar things and find out in what way they're similar, find out what they have in common, and extract that. So you identify the commonalities, and you pull those out. Those are a pattern of some kind. In OO programming, you might call it a design pattern, but it's just a kind of familiar idea of abstraction. It's what computing is all about. You identify what they have in common, and you name that. You say that the common stuff is this, and then the varying stuff is somewhere else. You separate the common from the varying. And the beauty of that is that you can reuse the common stuff in many different circumstances, just by putting it together with different varying stuff. So my evaluation interpretation and my print interpretation are both rather similar. If you look at the programs, let's go back to the programs. So from the deep embedding, here's eval. It's got two equations, one for val and one for add. And in the val case, you have to do something with that integer. And in the add case, you make recursive calls on the two sub-expressions, and then you do something with those two results. Here's the semantics for print. There are two cases, one for val, one for add. In the val case, you have to do something with that integer. And in the add case, there are two recursive calls on the two sub-expressions, and you have to do something with those two results. So there's commonalities there, and the idea is to express that commonality without getting bogged down in the differences. So the commonality of these three things here, semantic domain, an interpretation of values, and an interpretation of addition. So we have to somehow. Now, one difference between a val and print, which I didn't say, is that the val gives you an integer, print gives you a string. So that's another difference. Another difference between a val and print is that a val uses the identity function on the val, and print uses the show function. And the third difference is that evaluation uses integer addition to the add constructor, and print uses string concatenation with pluses and parentheses. So there are three differences. There's a difference between them in semantic domain. Eval and print have a different semantic domain. There's a difference between them in interpretation of values. Eval and print interpret the values differently. And there's a difference in the interpretation of addition, the binary operator. Eval and print have a different binary operator. So the name of the game now is that we're going to take these interpretations that are apparently different, the eval interpretation and the print interpretation. They're different, but they're overlapping. They're different, but they have something in common. So we want to express what they have in common and also express the different bits. So here's how to express the different bits, and then I'll show you how to express what they have in common. So the different bits are these three, and I'm going to call that an algebra. Why do I use a scary word like algebra? Well, it turns out that there's good mathematical reasons for this. This really does correspond to algebra in the sense you studied it in high school. I'm not going to explain why, but you can ask Josh later. He can tell you. So there is a formal mathematical reason why these things are called algebras. But if you like, you can just call it a thingy. That will work too. So an expression thingy for a semantic, so it consists partly of a semantic domain, and that's a parameter to the thingy, and then of two functions, and that's the other two bits. The interpretation of integers, and that's a function of type integer to a, whatever your type a is, and the binary operation on a's, so that's a function from a to a to a. So that's the differing bits. Eval and print are different, and the difference is expressed by having two different algebras, two different expert thingies. And now here's the trick. The shallow embedding, I need to, so it's now a parameterized type, and basically it's parameterized by one of these algebras. Very jolly. So I need to express this semantic domain, and I need to have this pair of a unary function and a binary operator. And so I'm going to do it as this type here. It's a slightly clunky way of doing it. You might expect there to be an expression to be a triple consisting of the type and two functions. And I can't really do that in Haskell. So I'm having to do it in a slightly non-obvious way. But if you were doing it in Agda, then you really could have a triple consisting of a type and a unary function on that type and a binary operator on that type. You really could have triples consisting of a type and a function and a function. Dependently type programming would let you do that. Haskell doesn't let you do that, so I need to do it in a slightly different way. But think of these things as being triples consisting of, well, yeah, slightly different from that too. So my interpretation is one of these. It's my shallow embedding is now as it's not as an integer and it's not as a string. So here we had where are we? Here the interpretation is an integer. Here the interpretation is a string. Here the interpretation is a pair with an integer and a string. Now the interpretation is a function. A function? What's going on here? It's a parameterized interpretation. The interpretation says, well, I don't know what my semantics is. But if you give me a hint, then I can tell you what the semantics is. If you tell me how, then I will tell you what the semantics is. And what does telling me how involve? Well, it involves specifying the varying bits. So the semantics of the expression now is the common bit, and then in order to finish off the job, you need to say what the varying bits are. You need to say whether it's evaluation or whether it's printing or whether it's something else altogether. So to express that, you give an expert algebra A, and so the interpretation is something that you give it an expert algebra A, and it gives you back an A. So it's sitting waiting for you to give it the rest of the story, and when you give it the rest of the story, it'll say, okay, well then the semantics is 12, or okay, and then the semantics is this string with 9 characters. But we just play the same trick as before. We follow the same pattern. This is my semantic domain. I need to say how to implement val and how to implement add. Val is supposed to take an integer and produce one of these representations. Add is supposed to take 2 of these representations and produce one of these representations. And this time the representation is a function. So val takes an integer and produces a function, and add takes 2 functions, x and y, and produces a function. So I'm not going to go through these functions here. They involve lambda expressions. Did you do lambda expressions? Yes, right, good. So there's nothing magic going on here. These are functions that take a pair and do something. And I'll let you meditate on these and verify that they're doing the thing you expect. The whole program is there. There's nothing missing. So this is the program. And once I define val this way and add that way, then I can make expressions in just the same way as before. So this add val 3, add val 4, val 5 is again an expression. So the same interface to this language works as before. But now E builds up one of these shallow embeddings, which is one of these functions. What can I do with that? It's a function. I can't print it out. I can't print out a function. What am I going to do with it? Well, remember, it's sitting there waiting for you to finish off the story. You tell it which interpretation you wanted, and it will give you back the answer. So, here's one thing you could tell it. Here's an extra algebra of integers, and that's the evaluation algebra. Here's another thing you can tell it. This is an extra algebra of strings, and that's the print algebra. And if you take your E and give it the evaluation algebra, you say, here's the rest of the story, I want you to do evaluation. It says, okay, the semantics is 12. If you take the same E and give it a different, finish off the story in a different way, you get a print algebra instead. It says, okay, the semantics is the string of 9 characters, open parenthesis 3 plus, open parenthesis 4 plus, whatever. So it's a bit like these, I don't know if you kind of choose your own adventure stories, or focus group testing of a movie. The movie production company, the studio, produces a film, and they produce 3/4 of the film, and they get a bunch of people to sit down and watch it, and then say, now what will make you happiest as an ending to this film? How would you like this film to end? And you get a whole bunch of opinions. You choose how you want the film to end. And then the studio says, okay, well that's the one we'll go and film. They find the most popular answer. They make the cheesiest movie they can, and it becomes a blockbuster because it's the one that's designed to satisfy the most people. That's what's going on here. This is the focus group approach. You produce most of the answer, and then you just need to say, how would you like to finish off the story? And if you say, I would like to finish off the story with an identity function and addition. I'd like to finish off the story with the integer type, the identity function and addition. Then the movie studio will say 12. That's what you wanted. And if you say instead, I'd like to finish off the story with the string type, the show function, and this funny binary operator that uses plus and parentheses, then the movie theatre says, the movie studio says, fine, this is the blockbuster that you wanted, and that's the one that we'll produce. So the varying bits now are one of these algebras, and an algebra is a pair of two functions. So in this case, the pair of two functions is the identity function and addition, and in that case, the pair of two functions is show and this funny binary operator here. But that's quite clever. So shallow embeddings, you have to pick the semantic domain, and it can be any semantic domain, but you have to pick one. But then you want it to vary. How can I do that? Well, you pick a semantic domain that is a higher order thing. It's a function. It's not just a value. It's not an integer. It's not a string. It's not a pair. It's a function. You pick the function as your domain, your semantic domain. And it's another way of looking at that is that it's a parameterized semantic domain. It's a function from some parameter to the eventual result you want. And the parameters are these pairs. So you plug in a pair, and then you get the semantic domain that you want. So this works only because we have higher order functions in our language. In order to do this, I need to be able to build a pair whose first component is the identity function and whose second component is the addition function. And I need to be able to build a pair whose first component is the show function and whose second component is this funny binary operator here. And I need to be able to build this E. And what's this E? Well, it's another funny function of this type here. There's lots of lambdas and F's and G's in. I can do this. I can do shallow embeddings. I can do parameterized shallow embeddings. But I can only do this in a language that has higher order functions. These higher order features are necessary. So if you don't have higher order features in your language, shallow embeddings are going to look very unappealing. How would you do this in Java? Well, Java's eventually, finally, going to have closures in, and you can maybe make this work. Similarly, if you don't have algebraic data types in your language, then deep embeddings are going to look very unappealing because you don't get a data type. You have to do something much clunkier instead. So this is why the OO programmers don't do embedded domain-specific languages so much. And it doesn't tell you why functional programs do it. Is this useful? But I think it is, and I think it's a very appealing, it's a very lightweight way of defining a new language. Of course, at the moment, it's a very basic language. It lets you do these addition things, so that doesn't seem like a very exciting programming language. And so the practicals that we're going to finish off the morning with are a slightly more exciting one. And then tomorrow I'll show you a more exciting one, but using the same idea. I could tell you. Let me tell you about these algebras briefly, because that's quite fun. But let me perhaps not do it in all that detail. Did you do FLOLAC'? No. Okay. So forget about domain-specific languages for the time being. This is back to ordinary functional programming. You can define a data type of lists. Finite lists of things of type A. So finite lists of integers, finite lists of strings, finite lists of characters, and so on. And there are two